Well, so let's give a formal description of this elimination method, Gauss-Jordan elimination method. Okay. So, yeah, first of all, we should define when we say that matrix is in its reduced echelon form. So, conditions are the following. First condition, any rows consisting entirely of zeros are grouped at the bottom of the matrix. Second, the first non-zero element of each other row is 1. This entry is called leading 1 or just leading entry. Next is the leading one of each row after first is positioned to the right of the leading one of the previous row. All other elements in a column that contain a leading one are 0. These are conditions that define matrix to be in reduced echelon form. So let's see which of these matrices are in reduced echelon form. Leftmost matrix, I think that it's okay, because we have 0 row. It is located at the bottom of the matrix, and 2 leading ones, and all other elements of a column containing leading 1 are 0. This is okay. And second is not, and you see why, because 0 row should be at the bottom of the matrix. Here we have second row is 0 row, and it is not on the bottom of the matrix. Okay. So this is not in REF. Yeah, shortly we say REF to reduced echelon form. And next matrix is okay, because you see this is we made this matrix many times. This is just identity I3 matrix augmented by column. This is reduced echelon form, obviously. And what about the last rightmost matrix? It is not in reduced echelon form. Why? Because of first non-zero element of second row. It is 3. First non-zero element of each non-zero row should be 1. So if you divide the second row by 3, you get a real reduced echelon form of this matrix. So some notions you should memorize during this Gauss-Jordan elimination method are elementary row operations. 3 kinds of operations you should remember. And another notion is reduced echelon form. I should know clearly. And what is reduced echelon form of a matrix? And also you should know the following. A reduced echelon form of a matrix is unique. So if you, for example, your teacher give you some matrix and ask you to find its reduced echelon form, then when students solve this, only one answer may be correct. You couldn't have 2 different answers to this question. Okay, brief explanation of Gauss-Jordan elimination method. So given a system of linear equations, you should write its augmented matrix and apply admissible row operations to get its reduced echelon form, and then write solution. Write a solution. So let's see the application of this method. In the case of this interesting, this is a little bit more interesting case than previous examples, because number of, how many equations we have here? 3 equations, but number of variables is more than 3. We have 4 variables, okay? And last column is, this is column of constant terms. Okay, so what we do, we see that leftmost top entry of this matrix 0, so we have to apply some interchange. You can, for example, interchange first row by second one, okay, and then next divide first row by 3, because we are going to get reduced echelon form, and first non-zero entry of this row should be, of each non-zero row should be 1. So we divide first row by 3. This pivot, leading one. So divide the first row by 3, get pivoting element is 1, leading 1, and we use this 1 to make other entries of first column 0. We need only annihilate first element of last row, just subtracting from R3 minus 4 times R1. Okay, and we get this matrix. And again, we look for the first non-zero element of remaining rows, and we see it could be found only in third column. You can choose any one. Let's choose first non-zero element of second row. Again, to get 1, leading 1, we divide second row by 2. We choose it to be next pivot element. Divide second row by 2, and get the following matrix. Okay, now use this 1, this 1, second pivoting element, this one, create zeros in first and third columns, third rows of this column. So R1 plus R2, this is operation make the corresponding element of first row 0, and R3 minus double R2. You apply them and you get this. And now let's check if we got a reduced echelon form. No. All the leading elements are 1s, and the matrix has downstairs shape, okay? But if I look at the leading element of third row, 1, you see other elements are 2 and minus 1. We need to annihilate them. We need to change this 2 minus 1 by 0. Okay? And how to do that? R2 plus R3 and R1 minus 2R3. This is the last pivoting element. And we get this. And you see, last matrix is reduced echelon form of initial matrix. Okay? And it remains to write solution. And look, we divide the variables in two kinds. First kind of basic variables, they are corresponding to leading elements x1, x3, and x4. And one variable, x2, it is called free variable. It's free variable because it doesn't correspond to any leading element. So you can write the following. x2 may take any real value. For example, x2 is r, and express that via x2 all other variables, x1, x3, x4. Oh, yeah, this is about just okay. Let me write here the solution indeed, because this example was about just finding a reduced echelon form. I just like to write also solution. It's not difficult. It's not difficult. Okay, so let me write. So x1, this is basic variable. This is 17 minus t. Let we use parameter t. x2 is t. It is free variable. May take any real value. Let it be t. And x3 is minus 5. And x4 is minus 6. This is solution. So what we have for this system? We see that infinitely many solutions. This system has infinitely many solutions because t parameter t may take any real value, and that's all. Let's see this example. Again, we write augmented matrix, make first non-zero element to be 1, and this will be leading 1, and use this 1 as pivot, and annihilate other entries of first column, choose next non-zero element, first non-zero element of second row, it is 1, it's ready already, just use it to clean second column, R1 plus R2, R3 plus double R2, and you get this. And we get REF. Again, we can write solution. Yeah, you should check which variables are basic, x1 and x2, because they corresponding some leading ones. And x3, it is free. So idea is to write just solution as via this x3. Yeah, for example, you may write, let x3 be r, some parameter, and express other variables x1, x2 via this r. So x1 will be minus 3r plus 4, x2 is minus 2r plus 1. This will be solution. Again, we have infinitely many solutions to this system. Next example, again, we write augmented matrix, make first non-zero element be 1 of the first row, use this 1 as pivoting element and clean first column. Okay, luckily together with first column we cleaned second one also. Now next pivoting element will be chosen from third column. It is 3, make it 1, dividing second row by 3. Okay, and use this 1 to clean third column, easy, R1 minus 6 R2, R3 plus 3, R3 plus 3 R2, and you get this matrix. And the last pivoting, last leading element is ready, 1. This is for first non-zero entry of third column. Use it to clean fourth column of this matrix. Okay, and you get this is already reduced echelon form, and we can write answer. x1, x3, x4, they are basic variables, and x2 is free. Okay, so we put x2 is r, and what is x1? x1 is, please imagine any time when you write solution that each row corresponds to equation. For example, first row, 1 minus 2, 0, 0 minus 2 means that x1 minus 2x2 is on the right side is equal to minus 2. Okay, so when you move this minus 2x2 to the right side, you change sign and you get this. x1 is 2r minus 2, x2 is r, this is free variable, x3 is 6, x4 is 1. Again, because of r may take any real value, we have this system has infinitely many solutions. Next example is again system having consisting of 3 equations in 5 variables. Okay. A large number of variables. Okay, again we choose first non-zero entry of first column to be pivot and clean using it first column, and together with first column will be cleaned also second and third columns. And we look for the next pivoting. It is taken to be first non-zero entry of last row. It is 2. To get 1, we divide last row by 2. Okay. Just interchange. Swap the second and third rows. Because this is construction of, I said this is stairway shape. Downstairway shape should have the reduced echelon form. So we have to interchange these rows, second and third. And divide the second row now by 2, get the first non-zero element is 1, and you use this 1 as pivoting element, subtract from first equation, first row, second row, multiply by 3, and last pivoting will be first non-zero element of third. What we do? R1 plus 5 R3, R2 minus 2 R3. And we get this last matrix is in echelon form. How many free variables we have here? x2, x3, they are free. x1, x4, x5, they are basic. Okay, so also think that these 2 free variables, x2 and x3, they are independent. So you have to use different letters for parameters. For example, st or rs and something like that. Okay, so let's use x to be r, x3 is s, then we express via this rs other variables, basic variables. x1 is minus 2r plus s plus 3, x4 is just minus 1, and x5 is 2. Again, we have here many solutions. And what is the difference, the structure of this solution from the previous ones? In previous systems, set of solutions has only one free parameter, t, for example, or s. And in this sense, we say that the set of solutions is one-dimensional. Here we have two independent variables, r and s. So because of this, sometimes you can say that, yeah, set of solutions, it is two-dimensional. Dimension of set of solutions is 2. And yeah, usually when number of equations more than number of variables, usually we get a system with inconsistent. Also, I forget to say that if system of linear equations has no solutions, then we say that system is inconsistent. If it has at least one solution, we say that system is consistent. Don't forget about this. Consistent system, inconsistent system. So let's see this example of inconsistent system. So we have this matrix as augmented matrix. Use first non-zero entry of first row as a pivot. Clean first column. Then find that the first non-zero element of second column is on third row, so we have to interchange second and third. Now divide second column by 3 and get first non-zero entry of second row is 1. Use this one to clean second column, R1 plus R2, R4 minus 2R2. Okay. Now choose first non-zero element. It's likely it is 1. Non-zero element of third row as pivot. Use it to clean third column. And we get the following. Look, we get row where all the entries except the last one are 0. Look at the last row of this matrix. Yeah, you can divide it by 13 to have REF, but indeed you needn't, because getting this kind of row where all the entries except the last one are 0, this means that you get equation 0 is, in our case, 0 is 13. This is impossible, so you just write the system has no solutions. So that's all. So this is the case of inconsistent system. Yeah, this last operation is applied to get REF. And the also explanation what we get after all concerning the last row. It is just 0 equal 1. It is impossible. It's impossible. And we say that system is homogeneous if all the constant terms are 0. Okay. Examples. And obviously, each homogeneous system consistent, because there is at least trivial solution. When all the variables are 0. Okay. So again, theorem 1.1 is saying a system of homogeneous linear equations always has the solution, zero solution, this solution is called trivial. So always consistent. So of course, when we study homogeneous system of linear equations, we're interested if system has non-trivial solutions. Okay, we're looking for the non-trivial solution. Again, to see that, we apply Gauss-Jordan elimination method. Yeah, you can apply. You can apply because later on we will see some better method which is called Gaussian elimination method. It is also presented in your main textbook. You'll see. Okay. So in this example, you have a system of two equations in three variables. Obviously, it is because it is homogeneous. It is consistent also because of number of variables, more than number of equations. It has many solutions, and you see, applying method to get REF. Yeah, you'll see this is REF. This is REF. I think that you know how to get this REF. Easy. And now we can write solution. X3 is free, so we write this and express other basic variables x1, x2 by this r. x1 is minus 3r, x2 is 4r. Yeah, this can be expressed as theorem. A system of homogeneous linear equations that has more variables than equations has many solutions. This is well-known fact from linear algebra. Okay, so let me show more effective than one method which is more effective than Gauss-Jordan elimination method. It is called Gaussian elimination. As I said, it is presented in your main textbook. Okay, and it consists of two stages. Again, your aim is to get from augmented matrix of the system of linear equations to get reduced echelon form, but you first try to get its echelon form, and then using backward substitution to get its reduced echelon form. It's better if you apply some computations of operations, some estimation of operations using some ideas from complexity theory. You'll see that Gaussian elimination is better than Gauss-Jordan elimination method. Okay, so let's see first, what is the echelon form of a matrix? Look at here, again we have some conditions. First condition is zero rows, they are at the bottom of the matrix. Again, first non-zero element is 1. Again, it's called a leading 1. And third condition is again the same, leading of each row after the first is positioned to the right of the leading one of the previous row, and so on. And we just ignore the last condition where it was said that if some column has leading 1, then all other entries of this column should be 0. We ignore this. We don't ask this condition for echelon form of the matrix. Okay, so let's see some example how we solve this system using Gaussian elimination method. Look here. Beginning is similar. So imagine as if you do. We are going just one direction. In one direction to get from top to bottom to get echelon form, and then backward direction to get from echelon form reduced echelon form. So let's first try to get echelon form of the matrix. Leftmost top element is 1, it's okay. Use it to clean first column. Then we look for the next pivoting and use it only for bottom rows for R3 and get this. And the first non-zero element of third column is 2, divided by 2 and get leading 1, and we get echelon form. This is echelon form. Now we go from bottom to top. So we use, So first is just explanation, the idea in the language of equations to see. And then we do the same in the language of matrices. So look, what is the echelon form is corresponding system is written on the first lines of this slide. Okay, then you see x4 is already defined, it is 2. Now in x4 we can write what is x3? x3 is minus 5. Now you know x4 and x3, then you can just get from first equation the following. And you see that x2 is free, so you just put x2 is r, some parameter, real parameter, and express the solution via this parameter. x2 is r and x1 is minus r plus 10. Now we do the same in the language of, sorry. Yeah, back substitution. Okay. Yeah, this is another example just because I think that this is another example. Again, okay, so we write augmented matrix, apply as in, this is similar, a little bit similar to the case of Gauss-Jordan, but we go in one direction from top to bottom, get echelon form, and then we use this one to clean fourth column of this matrix. Look here. You see, yeah, we use this. This one to clean fourth column. Yeah, you know what to do. R1 minus 2 R3, R2 minus 3 R3. And you get this. Now you use next pivot, this one, to clean third column. Easy. R1 minus 3 R2. You get this. And indeed, we already get REF, reduced echelon form. So you can write answer. So please try to remember this moment. So first you go from top to bottom, applying the same ideas as in the case of Gauss-Jordan, but never you turn back one from top to bottom to get echelon form. And then after getting echelon form, you change direction to the opposite one and go from bottom to top. This is idea. This is the idea of Gauss. So this is called Gaussian elimination method. It is more effective than Gauss-Jordan elimination. I hope that maybe later on I'll give an explanation of that. Maybe even from this example you realize, yeah, this is much better than Gauss-Jordan elimination. And when you get REF, this one REF, you can write the answer. You see here basic variables are x1, x3, x4, and the free variable is x2. Let x2 will be r, then x1 is 10 minus 2r, and x2 is r, and x3 is minus 5, x4 is 2. This is a solution. Yeah. Indeed, we have infinitely many solutions because of presence of parameter